America may be heading toward an electricity shortage while thousands of proposed power projects are waiting for permission to produce it. Across the country, developers have secured land, raised capital, ordered equipment, and lined up customers for new solar farms, batteries, wind projects, and power plants. But many of them cannot connect to the grid, not because the technology does not work, not because America lacks energy resources, and not necessarily because the projects are too expensive. They are trapped inside an obscure engineering and regulatory process that can take years, dramatically increase costs, and kill otherwise viable projects before construction even begins. At the end of 2025, more than 2,000 gigawatts of proposed generation and storage were actively seeking grid interconnection in the United States. That number is larger than the country's existing power system, but it does not represent electricity America can actually use. Because before a power plant can serve a data center, semiconductor factory, steel mill, or American city, engineers must determine whether the grid can absorb its output, which equipment must be upgraded, and who will pay for those upgrades. And as electricity demand accelerates, that process is no longer just slowing renewable energy, it is beginning to determine where America can build factories, where AI infrastructure can expand, and whether the country can turn its energy resources into industrial power. The massive energy bottleneck is not producing electricity, it is getting permission to deliver it. For much of the past 2 decades, American electricity demand grew slowly. Utilities could plan around relatively predictable consumption, replace aging equipment gradually, and add generation without expecting sudden changes in regional load. That era is ending. Data center electricity use has expanded rapidly, and federal estimates have warned that it could double or even triple from recent levels within only a few years. Advanced manufacturing is adding another source of large, concentrated demand. A single major data center campus, semiconductor complex, or metals processing facility can require as much electricity as a small city. These are not ordinary customers. They cannot wait for power only when the sun is shining or when regional demand is low. They need high-capacity connections, dependable supply, voltage stability, backup options, and confidence that more electricity will be available as they expand. This is why the interconnection bottleneck is no longer just a renewable energy issue. Solar, wind, batteries, gas plants, and eventually new nuclear projects all face some version of the same question. Can the network absorb their output without creating dangerous overloads or forcing expensive upgrades elsewhere? And now large consumers face a parallel problem. A state may announce a multi-billion-dollar factory, but the local utility may not be able to serve it on the promised schedule. A data center developer may secure land and tax incentives, only to discover that the transmission system needs years of reinforcement. Industrial policy can attract the investment. The grid still has to deliver the electricity. To understand why this takes so long, it helps to understand what connecting a power plant actually means. The electric grid is not a collection of independent wires. It is a synchronized machine operating across vast distances. Electricity flows according to physics, not commercial contracts or state boundaries. When a new generator begins injecting power at one location, the effects can spread across multiple transmission lines and substations. Engineers must determine whether existing equipment can carry the new flows, whether voltage remains within acceptable limits, and whether the system can survive the sudden loss of a major line, transformer, or power plant. They must examine short-circuit levels, protective relays, thermal limits, stability, reactive power, and contingency performance. A project that appears harmless during normal operation may create a serious problem after another component fails. And because grid operators are required to plan for credible failures, the project cannot simply be plugged in and tested later. The risks are too large. So a developer submits an interconnection request. The transmission provider or regional grid operator places the project into a queue. Engineers then study how the proposed facility would affect the network. They identify upgrades that may be required: a new substation, a larger transformer, higher capacity conductors, additional circuit breakers, voltage support equipment, control systems, or an entirely new transmission line. Then comes the most important question: who pays? In many parts of the United States, the new project can be assigned a large share of the cost of upgrades triggered by its request. That sounds reasonable. If a generator creates a problem, the generator should help solve it. But the reality is more complicated. The new project may not be causing a healthy grid to become weak. It may simply be the first project to reveal that the regional network has been underbuilt for years. Imagine a developer proposing a solar and storage facility in an area with strong resources but limited transmission. The generation itself may be economical. Then the study finds that connecting it would require a major substation expansion and reinforcement of a distant transmission corridor. The upgrade could cost tens or hundreds of millions of dollars. Suddenly, the project is no longer competitive. The developer withdraws, but that withdrawal changes the assumptions used in studies for every project behind it. Power flow patterns change, cost allocations change, some network upgrades are no longer required, while others become larger. Engineers may have to repeat part of the analysis. Now the next project receives the bill. It may withdraw as well. This is one reason the queue became self-reinforcing. Long delays created uncertainty. Uncertainty encouraged developers to submit requests at multiple locations to preserve options. More requests increased the study burden. As projects withdrew, the remaining studies had to be revised. The queue became less like an orderly construction pipeline and more like a crowded market for possibilities. That distinction matters. 2,000 gigawatts in a queue does not mean 2,000 gigawatts of power plants are ready to build. Some projects lack financing. Some are competing versions of the same development. Some depend on uncertain contracts or incentives. Others are located where the grid cannot support them economically. But even after weak proposals are removed, the central problem remains. Viable projects can still be delayed by a process that was not designed for this volume, diversity, or speed of development. Historically, many projects were studied one at a time in the order they entered the queue. That approach worked better when the system was processing a smaller number of large conventional power plants. It works poorly when hundreds of solar, battery, wind, hybrid, and gas projects arrive across the same region. Federal regulators have responded by requiring a shift toward cluster studies, where groups of projects are analyzed together. The reforms also add stricter readiness requirements, financial commitments, deadlines, and greater transparency. Federal Energy Regulatory Commission. The basic logic is sound. Study projects as a group. Discourage speculative applications. Use realistic operating assumptions. Give developers better information before they enter congested areas. But procedural reform cannot create physical capacity that does not exist. A faster study may still conclude that a new transmission line is needed. A more accurate model may still identify a transformer shortage. A project may receive an agreement and then wait years for permits, equipment, construction crews, and rights of way. The bottleneck can move without disappearing. This creates a deeper conflict over the purpose of the grid. Project developers argue that they should not be forced to finance broad regional infrastructure through a single interconnection request. They say the network upgrades often benefit future generators, consumers, and reliability across a much larger area. Utilities and transmission owners respond that existing customers should not automatically pay for speculative projects that may never be built. Both arguments are valid. If costs are placed entirely on the first project, the first mover may withdraw and the upgrade never happens. But if costs are broadly socialized, consumers could be charged for infrastructure built around projects that later disappear. The United States has struggled to resolve this because the benefits of transmission are widely distributed, while the decisions are fragmented. One state may host the power plant, another may host the transmission line. Consumers across several states may pay for the upgrade. A factory hundreds of miles away may benefit from the added reliability. Different utilities, regulators, regional operators, landowners, and local governments can all influence the result. Electricity crosses borders instantly. Institutions do not. That fragmentation is becoming strategically important because the next industrial competition will be power-intensive. Artificial intelligence is not only a software industry, it is an electricity, cooling, semiconductor, and infrastructure industry. Battery production is not only a manufacturing process, it requires dependable power, refined materials, chemical processing, and logistics. Advanced metals, critical mineral refining, defense manufacturing, and clean industrial processes all depend on the ability to connect large facilities and new generation faster than competitors. China's energy system has its own inefficiencies, overbuilding, regional imbalances, and curtailment problems. It should not be treated as a frictionless model. But China has repeatedly demonstrated the ability to build generation, transmission, industrial parks, and supply chains at enormous scale. Its system can align infrastructure with state industrial priorities more directly than the fragmented American model. The United States has different strengths: deeper capital markets, strong engineering firms, innovative developers, advanced software, abundant energy resources, and a legal system that protects private investment. But those strengths do not automatically produce infrastructure. A country can announce factories faster than it can energize them. It can offer tax credits faster than utilities can expand substations. It can develop world-leading energy technology while forcing projects to wait in studies based on an increasingly congested network. That is how an administrative process becomes a geopolitical constraint. Still, the interconnection queue should not become a convenient villain. Grid studies exist for a reason. Connecting projects without careful analysis could create overloads, unstable voltage, protection failures, or higher costs for consumers. Speed is not useful if it undermines reliability, nor should every queued project be treated as essential infrastructure. A disciplined process should reject projects that are speculative, poorly located, technically unrealistic, or unable to demonstrate financial readiness. The goal is not to approve everything. The goal is to identify viable projects earlier, plan shared infrastructure before individual requests trigger a crisis, and use the existing network more intelligently. That means regional transmission planning must be coordinated with expected generation and load growth. It means cost allocation must recognize when an upgrade provides broad system benefits rather than serving only one developer. It means grid-enhancing technologies, advanced conductors, dynamic line rating, storage, and improved power flow controls should be used where they can safely increase the capacity of existing assets. It also means rethinking how projects use their interconnection rights. A solar plant and a battery may be able to share a connection without exporting their maximum output at the same moment. An existing generator site may support replacement capacity more quickly than an entirely new location. Large consumers may bring on-site generation or flexible demand that reduces pressure during critical hours. None of these solutions eliminates the need for new transmission, but they can make the system more selective, efficient, and realistic. America's energy debate often focuses on what should be built: more solar, more gas, more nuclear, more storage, or more transmission. The interconnection crisis reveals a more fundamental question: can the country convert proposed infrastructure into operating infrastructure? A power plant without a grid connection is not capacity. A battery waiting for a study cannot support reliability. A factory without an energization date is not industrial strategy. And a queue containing thousands of projects is not the same as a functioning expansion plan. The United States is entering an era in which electricity will influence where AI systems are trained, where semiconductor plants are built, where critical materials are processed, and which regions capture the next generation of industry. Winning that competition will require more than producing equipment or offering subsidies. It will require institutional speed. It will require engineers, regulators, utilities, developers, and states to plan the network as a system rather than treating every project as an isolated request. Because the massive energy bottleneck no one is talking about is not simply a shortage of electrons. It is the invisible system that decides whether new power can reach the grid, whether the grid can reach new industry, and whether an American energy project becomes real or remains trapped in a spreadsheet.